Alright, so in this video we're going to continue our conversation. So looking at using the t-distribution, but now looking at how that's going to affect a confidence interval for a mean. So we're going to first talk about the idea of the formula before we actually go back and look at the conditions. This is what our formula is going to look like for a confidence interval for the mean when our population standard deviation is unknown. What I'd like to do is compare this formula to what our formula looks like when we were doing it for a categorical variable for a proportion. So this was our confidence interval for a proportion, and so when we compare the two intervals, which this one's also right down here, that's the new one, it seems like a pretty big difference, but not really. So p hat was our sample proportion, y bar is our sample mean. So proportions are for categorical variables, means are for quantitative variables, but still a sample value that we're starting with. Up here, the next thing we had was a z. Z would told us how many standard deviations we needed to be from the mean. This was based upon our confidence level given to us in the problem. T is also going to give us a measure of how many standard deviations away we need to be. It's going to be based upon our confidence level as well. The only thing new with finding T is, as we talked about with the t-distribution, the spread changes based upon our sample size. So we're going to have this extra piece of information, that degrees of freedom that we saw with the hypothesis testing, with the same degrees of freedom based upon our sample size minus 1. Where did z come from? A table. T is also going to come from a table. So we'll see what that looks like here in a moment. This square root part that we had up here was our standard deviation of p hat. And down here, this s, or the square root of n, is going to be our standard deviation of y bar that we're going to work with. Except remember, we had s in place of sigma. So it is following a very similar process to what we have already seen. So now let's talk to the other parts that are different. So our conditions are the same conditions that we actually had for our hypothesis test. So that's not going to be new. And then we just got to interpret. So conditions, calculation, interpretation. Let's also go ahead and look at this table so we understand how that is going to work. Right, so this is what our table looks like. So we have degrees of freedom. This is our sample size minus 1 that we've been talking about over here. And then we have our confidence level here at the top. And so we'll just be matching things up. So if it says I'm 95% confident, I'll be in the 95% column. And then I just got to go down that column until I find my corresponding degrees of freedom to go along with it. As you scroll all the way to the bottom, what you'll actually find is this last row, where our degrees of freedom is at least 100. All of these numbers you see down here are basically the z equivalent. So if you remember when we did 95% confident for our z, that was a z of 1.96. So that's how you see that t, as our sample size gets bigger and bigger, that spread becomes basically what it is in a z and gives us the same values as our z table would. Alright, so we will be doing these calculations by hand. So we're just going to start by then looking at an example. Alright, so we have a company that is interested in estimating the annual mean out-of-pocket employee health expenses of their employees. So they took a random sample of 66 employees, so that's going to be our n, and found that the mean out-of-pocket employee expense for the year was $1,752. So that's going to be our y bar, with a standard deviation of 1,186. And again, notice this number is coming from just those 66 employees. That's why it's a sample standard deviation and not a population one. We're going to create a 95% confidence interval for our parameter here. Alright, so for our first step, we're going to check our conditions here. So first, checking to see if we have our random sample. And it just says I took a random sample of 66 employees. Again, don't know how they actually chose those specific 66 people. So for, again, from at least what I know, there's no known bias here. And then we either need to have it normally distributed or have a sample of at least 30. Reading the problem, it doesn't say anything about it being normally distributed. I don't have a histogram to look at to see if it looks symmetric and bell-shaped, so I don't know anything about that. But I do have a sample size of at least 30 because my sample size is 66. And then finally, our population standard deviation is going to be unknown. And again, remember, we have a sample standard deviation. It's just not the population one. Alright, for step 2, we want to do our calculation. So if I look at my formula I'm going to use, I already know y bar, s, and n. I just need to find t. And so t is going to be based upon our confidence level. So it said we're going to use a 95% confidence level. And then we need our degrees of freedom, which is our sample size minus 1. So my degrees of freedom is going to be 65. So these are going to be the two numbers that I'm going to go to my table with. This one's going to tell me which column to go to again. This one's going to tell me which row to go to. So we look up our table. Here's my 95%. Now I'm trying to find 65 degrees of freedom. And what you'll notice is I can't find 65. So I found 60, and I found 70. Now from a general standpoint, I don't generally care if my students use either of those numbers because that means you're in the right place. However, students usually like to know why I do what I do. So I'm always going to round down my degrees of freedom. So even though 65 under normal rounding circumstances would round up to 70, if I round down to 60, what I'm doing is underestimating my sample size. First, if I round up, I'm overestimating my sample size. I'm saying I have more data than I actually do. So I find it safer for me to underestimate my sample size. And so I'm going to use the t of 2 for our example. Again, that number is just coming from the table. Then we do have everything to plug into our formula. So we have our sample mean, we have our t, we have our s, and we have our n. And then we can do the same thing on the other side. Alright, then again, just doing our math, so making sure we get our order of operations correct. I'm going to take the 1,186 and divide that by the square root of 66. And of course, do that on both sides here. Then do my multiplication and divide. So my multiplication here. I get my 291.97. And then finally our subtraction and addition. Here I rounded to 2 decimal places since we're talking dollars. So there would be my calculation done. This is a reminder of some terms. This 145 number is what we'll refer to as our standard error. And this 291.97 is what we refer to as a margin of error. Okay, so finally we're going to interpret. So I am going to be 95% confident that the population mean annual out-of-pocket employee health expenses. Is between our two numbers. Between our $1,460 and our $2,044-ish dollars. Now, just a couple of reminders about some other things. So a big kind of note that I'm going to write here. So realize at first that this is not telling us about individuals. That's what Chebyshev's rule does, not this. So a very important term that we're doing inside this interpretation, right? This is a mean that we're talking about. This is where the mean health expenses fall, not necessarily individual health expenses. Right, if students were to ask me for a different example, I would say, well, let's talk about like the scores on an exam. Right, if I tell you that I think the mean is between a 70 and an 80, that doesn't mean that I think every single student is scoring between a 70 and 80. That's what the mean is going to turn out to be. But individual student scores are going to look a little bit different than that, and that's where Chebyshev's rule would be helpful for me. Another just reminder. So if you notice that our interval here is kind of wide, it's about $600 wide. So how could I actually narrow this interval? So there were two different things that we talked about that are able to make our interval more narrow. The one thing that we can always do is increase our sample size. The more data we collect, the better job at estimation we're doing. Again, assuming we're doing things in an unbiased fashion there. Other thing that we can do, which is not as good, right, is to decrease our confidence level. So instead of being 95% confident, I can be 90% confident instead. The last thing I'm going to show you is, even though we do this by hand, you could actually still use StatCrunch to kind of show that you get the same numbers. So if I pulled up my StatCrunch, we're going to go to the same place that we were for the hypothesis test. So I'm going to go to Stat, T Statistics, one sample with my summary. And just as before, I'm going to enter in all my values. So my sample mean was 1,752. My sample standard deviation was 1,186. And our sample size was 66. Instead of doing the hypothesis test, I can just click my confidence interval button. And then here I could change my confidence level to something else, but we're doing that 0.95. And so I'll just leave that as is. And then I can hit compute, and you'll see some numbers, which might not be perfect if we do some rounding along the way, but we're pretty close. So here they got the interval was $1,460.44, which again, we're a little bit off because we rounded some numbers along the way. Remember, especially when we went to the table, we couldn't find the exact T that we wanted. And their upper limit they got was $2,043.55, which we got 97 cents. So notice ours is a little bit different than what we got here. Also, what you'll see here is that standard error that we talked about. So it was 145.987 that we had. So notice that that's that number that we got right here. So sort of a nice way of checking to make sure you've done your calculation correctly by checking StatCrunch and seeing how close your numbers are to what you got there. Alright, so hopefully after this video, doing a confidence interval for a mean makes sense. The last video for this unit, we will talk about determining sample size now that we're working with a quantitative variable.